Okay, so let's study now buoyancy. And buoyancy is the force that objects would feel when they are submerged in water. So to start studying this effect, let's consider a cylinder, right? We have a cylinder here submerged in water. So you know that pressure increases with depth. So this size down here is deeper than this size here on top. So therefore, the force up here due to the pressure is going to be greater than the force down, pushing down here on the top. That's going to give you a net force pointing upwards, simply because this side is higher than this side here at the bottom. So then you get a net force, and we call this force buoyant force. And it's equal to the force pointing up minus the force pointing down. So let's see how big this force is. Imagine that I have this shape here, right? This is an imaginary shape. So there's some liquid inside this shape. And what is the net force in this liquid? Well, this liquid is not moving upwards or downwards, right? It's just staying there at equilibrium. So therefore the net force is equal to 0. So that means that the weight of this liquid enclosed in this surface has to be equal to the buoyant force. Now if we just remove the liquid and place some object there with the same shape, what has changed? Well, the force, the buoyant force, depends only on the water on the surroundings. It doesn't depend on what it was inside, because that's what we were studying. So therefore the buoyant force is going to be the same. The buoyant force then is the same as the buoyant force that the liquid it displaces. So this buoyant force is going to be the same as the amount of liquid that it was displaced here. And we'll make sense of that phrase in a little bit. So buoyancy, when an object or a portion of an object is immersed in a fluid, it displaces fluid, right? It displaces some water, some liquid. The displaced fluid's volume equals the volume of the portion of the object that is immersed in the fluid. So then we have Archimedes' principle, which says a fluid exerts an upward buoyant force on an object immersed or in or floating on the fluid. The magnitude of the buoyant force equals the weight of the fluid displaced by the object. So this is the equation here. So the magnitude of the buoyant force, this force here on an object that is immersed, is equal to what? Is equal to the volume of the fluid that is displaced times the density of that liquid times gravity. This is what this here is. This number here is. This is the mass of the liquid that was displaced, and this is simply mg. This whole thing, right? So this is mg. So therefore, this buoyant force is equal to the weight of the fluid that was displaced. Let's look at a question to see if we understand this. We have a heavy lead block and a light aluminum block of equal sizes, and they are both submerged in water. Upon which is the buoyant force greater? On the lead block, on the aluminum block, or they both experience the same force? And the answer is C, simply because they both have the same size, right? So they displace the same amount of water, and the buoyant force only depends on the amount of water that is going to be displaced. Let's look at a simple problem here. We have this is water, and then there is this wood inside the water attached to a string, and we want to calculate the tension on the string. So what are the forces acting on the block? Well, the weight of the block, the buoyant force, and the tension. The size of the block is 10 centimeters by 10 centimeters by 10 centimeters. That is the volume. And the density is 700 kilograms per meter cubed. Okay. So then we can do a free body diagram. So we can write that the buoyant force, this force, minus the weight, this is the mass of the wood, times G, minus the tension, that is equal to 0. Okay, so what is the buoyant force? Well, the buoyant force, we know, is the volume, is the mass of the water that was displaced times G. And the mass of the water that was displaced is simply rho 0, which is the mass of the water, or let's just call water here, the density of the water, times the volume that was displaced, which is equal to the volume of the wood, times G. That is this number here. And then the mass of wood, that is the density of wood, times G. So that is this equation here, this equation, and then we can find the tension from this equation. The tension is the density times the volume times G minus the density times the volume times G of the both water and wood, and then we can do some math here. So we get here the density of water, density of wood, and that gives you 2.9 newtons. So how do we find whether an object floats or sinks? Well, remember the two forces there are the buoyant force and the weight. If the weight of the object is greater than the buoyant force, the object sinks. If the weight is less, then the object floats. So remember, the buoyant force is equal to the density of the liquid times the displaced volume times G. And the weight of the object is just the density of the object times the volume times G. So it all depends. These two things are the same here. These volumes and this G are the same. This is gravity. So it all depends on the density. So if the density of the object is greater than the density of the liquid, then the object sinks. If it is less, the object floats. So this is the situation when it floats. This here is the situation when it sinks. Okay, two blocks, or another question here. Two blocks are of identical size. One is made of lead and sits at the bottom, on the bottom of a pond. The other is wood and stays on top. Which one has the greater buoyant force? And the answer is the lead block, because that is completely immersed in the liquid. So therefore it displaces more liquid and there's more buoyant force.